we're going to continue our lecture, and what I would like to accomplish today mainly is these things. Remember last week we talked about that every distribution you can turn them into PDF, and the PDF and CDF, just the integration, and then CDF, 1 minus CDF, you get your, well, let me come back here. The relationship between S and F, F and H, H and S. Oh, when I say H, you need to be careful. It's the small h, letter H, or capital H. Which one is accumulation over time? Big H is integration. And HT, if it's small letter, means at that very moment how much hazard you're going to have. So, you know, if I say this is a hazard for human age dependent, so H5 versus H45 means that at age 45 how dangerous it is, or H5 how dangerous it is. But if I use a capital H, that means that, oh, you've been in a very, you know, you live in LA. Air pollution's horrible, so you've been, you know, breathing that kind of polluted air for 45 years. How likely you will have asthma? Okay, and so all this relationship, we're gonna treat it like you already understand. So you should be able to do it, you know, later. Algebraically or using SAS. Okay, let me give you another pop quiz questions. For example, which one is a conditional value? Okay, which one is a conditional value? S, H, small letter H, or PDF, F? Which one is a conditional value? Okay, survival function, okay, is a conditional value. You cannot talk about survival, you know, until you pass that time. And H is also a conditional value. Because H is about how likely you will fail. So H and F, they are proportional, but you cannot talk about H, hazard function, unless you already survive beyond time t. You know, if I want to say, oh, how dangerous at age 45, but you only survive till age 40, you cannot at age 40 talk about that things. Okay, so those that got real world meaning. And now let me get into the other stuff. Okay, this is built on what we learned last week. Okay, so first, let me do this one. Here, I have an incremental time t for exponential function. So my ft is, you know, is a my small letter ft is a upside down function, right? My ft is this things, exponentials, this things, but my ft, capital Ft, is the 1 minus exponential things. And finally, what is my ht? Ht, look here, is equal to ft divided by st. And s is 1 minus f. Everybody see that? See that? But what is important here is that my parameter, I already set it up, the arrival rate at 2. So see what's ht? Ht is 2. Means what? No matter at any given time, you have the chance to get hit twice. And is this get hit twice? I don't care what kind of evil is this gonna hit you twice. Does it change over time? No, it's a straight line. That means that HT is memoryless. You're not going to have more hazard when you're young or when you're old. The HT is 22222. Same thing, if I change to 1, okay, then my FT is coming down like before, but since the here's 2, here's 1, so it's coming down much smooth or less dramatic like this one. So my FT is going up, less dramatic, and my HT is FT over 1 minus FT, so you end up with this green curve, and this time the green curve is not 22222, it's 11111. Okay, and finally I can have 1 star at 0.5. So my hazard FT drop like before. My FT grow to 1. But this time you see here about 3. I'm already about 4. I'm already reaching 1. Here, even I reach 5. I'm not reaching 1. I'll probably reach 1 or somewhere around 6 point something. Okay, and why? Because my hazard function now is discount again from 2 to 1 to half. It's 0.5, 0.5, 0.5. So everybody see that? How to generate the 3 things based on my exponential distribution. If everybody should be able to do the blue one and the red one based on our last 2 weeks exercise. The only things we generate new this time is the green function. Okay? And the green function is exact, since it's a constant, so this constant is your hazard function. HT equal to your constant. Equal to your constant. Everybody get it? Okay, yeah. And if you want to play with this, I probably will change this to 3, 1.5, and 0.75. Okay? Next, what if we're not doing exponential, we're doing YBO. So YBO is what? Is the exponential disguise. Okay, so let's just say that I change my scale function and my shape function accordingly. So T, this time I don't want to start from 0, I start from 0.0001, okay? And why I'm doing that, just make sure that it looks smoother. Okay, so Ft is this function. I have my scale and shape defined, and my Ft is this function, okay? And both follow this rule. Finally, okay, if my this is something I would like to show you here. I will turn this around. People, pay attention here. Okay? Which one you think that is exponential? When the shape value equal to 1, 0.3, or 1.5 is exponential. 1. Why? Because 1, you can see constant, no memory, 1, 1, 1, 1, 1. Exponential coming down, PDF, CDF going up, right? But, okay, so blue is going, I mean the hazard function, in this case, we look at it, okay? Hazard is even out, red even out, red going up, 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 and red coming down. Which one you think that the red will come down when the red, when the shape function greater than 1 or less than 1? Huh? See here? Shape equal to 1 is exponential distribution, is a constant. Shape greater than 1, the hazard will grow. When shape less than 1, the hazard will coming down further and further. Okay, young lady, you play soccer, so you tell me which one showing that the hazard is growing over the years. So the older you get, you should stay away from soccer. It's very, very dangerous. Soccer is for toddler, not for college kids. True? True? Okay, I apologize. I'm making fun. Which one you think is the dangerous when you get older to play? Well, I have to say, so both my kids play soccer when they were 4 or 5. Why? Because the center of gravity is very, very low, and then if they really get hit, they tumble and they get up, and it's not that bad. And the other thing is that actually, probably before 3 and 4, the gender differences is not that obvious. Boys and girls actually can play you don't need to worry about gender differences. But after that, it's not fair. Well, kids still, even kids, they have soft bone, they still can get hairline fracture. Okay, so you tell me which one shows that the hazard function said that this is not, which one is dangerous for adult, which one is dangerous for kids? This one is danger for kids or again danger for adult? Yeah, this one's adult. Okay, so now intuitively we really see Weibull function got a shape function. The shape function, when it's equal to 1, is equally dangerous, no matter how old or how young. Here, showing that hazard is getting more and more hazard when you get older and older. So this is something seniors should stay away from, right? And this is when you get older and older, it's getting less and less dangerous. Okay, so yeah, I would like you guys, Victoria, give me a Weibull, and don't use my scale function, don't use my shape function, shape value. You generate your own scale and your shape value, but generate some hazard is memoryless, constant hazard. Generate some hazard is monotonically increasing, and generate some hazard monotonically decreasing. Okay? And why this exercise? Just make you feel the math, the geometry and the real life data will be related. Okay? Next, okay? Hazard function could be constant hazard, could be hazard decreasing, could be hazard increasing. We already see that. In reality, there are hazard, the famous hazard we usually talk about is called bathtub shape hazard. Bathtub shape hazard happen to most of the biological system. Our survival rate is a lot less. We are more susceptible to disease and all kinds of stuff before we reach teen. But once you reach teen, you stabilize. Your hazard will get lower and lower. But then aging process, when you reach male or female, they now say even male got menopause, means that after 55-ish, geriatric medicine kick in. You need to worry about a lot. Well, aging process. Okay, how many people think that what's the #1 concern, safety concern, after menopause, or male or female after a certain age? Anybody know? Speculate. Heart is not as dangerous. I'll tell you what's the most dangerous. The grandma or grandpa, once they step out of their bathroom, slip, trips, and fall, a lot of times they have hip fracture. And once they have hip fracture, they stop playing golf, they start doing physical activity, and their quality of life drop dramatically. So a lot of aging process is not, why menopause is an aging issue is an index, because you will have calcium depletion and you need calcium supplement. If you don't have that, including men, sometimes your bone become very brittle. And if it once become very brittle, especially why people live in New England and New York, they like to move down here or even further down, is because during the winter time, they're gonna encounter black ice. And once you slip, trips, and fall, you will be your quality of life drop dramatically. Okay, so slip, trips, and fall actually more dangerous. I'm not saying heart attack is not an issue, but that is a big issue. So when I show you the bathtub shape, I don't want you to just think about, okay, there is a hazard mathematically gonna look like this. Actually, sometimes people will say that they will break it down. They will say that when you're young, the hazard function using, pediatrics used decreasing hazard, geriatric using increasing hazard to talk about that. But somewhere in the middle is kind of like, the hazard is not as bad, okay? So now you see why we need to develop HT. HT, really, we're not interested in HT itself. We're interested in, give me the data. I look at HT, I'll say, hey, what kind of shape? Increasing, decreasing, constant, upside down bell shape, or bathtub. Based on this, immediately I can say that, does that make sense? No? Do you think that some of the car we buy, Tesla these days, a lot of time, do you think car got bathtub shape, hazard function? When you're gonna see the car mechanics? At the very beginning, the first 6 months. Once you stabilize it, you got a decent car, not a lemon, you drive for a while. But then after a certain time, most of the car warranty expire, all the trouble is getting started, okay? So bathtub shape makes sense for all kinds of HT. Okay, and we're gonna talk about the hazard function by modeling the lifetime, but we can also modeling the hazard function, okay? And a lot of time, here I'm just trying to show you if I model as a hazard function. I basically said hazard is a constant, what we call H0T, baseline hazard, and after that there's exponential things. Inside the exponential, I got a lot of beta 1, beta 2, a bunch of beta. What's a beta? Usually we call it risk factor. So smoking is a risk factor, and if you smoke 1 cigarette, 2 cigarettes, depends on number of cigarettes, your beta times that through that exponential, your headlock hazard will increase accordingly. So in other words is that different risk factor will make your hazard function going up, 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 or coming down, down, down. So when we talk about survival analysis or reliability, what are we trying to figure out? Hey, how to control your risk factor? Something bad for you, we should eliminate it. Something good for you, we should increase that. So people talk about what? Red meat, high cholesterol food, stay out of it after a certain age, because that will make your hazard increase. And exercise, what they call the Mediterranean diet, a lot of olive oil is good for you, so take more of that, will make you live longer, right? And some things, people will say that, okay, what makes sense? Risk factor for your car, you change oil or not changing oil, you do alignment or you don't do alignment for your wheels, do you change, the air filter or clean air filter, fuel filter from time to time? Because if you do that, then your hazard will drop. If you don't do that, the hazard will increase. So we're basically, later on, we'll have two different ways to model these things. One is called life regression, means that we model what is good for your life. And we can also model what is bad, good for your hazard, good for your hazard, bad for your life. Good for your life, bad for your hazard. So in other words, since we already said it last time, survival function and hazard function, they're related. So you model one side, you should be able to get to the other side. And now the question is, why sometimes we want to model everything through hazard, sometimes we want to model some things through survival? Because certain parameters is hard to estimate one way or the other. And we basically said that, okay, I need to approximate this, and I'll explain some of the tricks insurance company or even airlines sometimes use, because they need to figure out that what is reasonable risk, what is not reasonable risk. Okay? So, if we do that, okay, we will end up with what we call proportional hazard. Is the following. Say I have sometimes we call it two cohort, C-O-H-O-R-T, two group of people, senior citizens, same age, same ethnic background, same salary, income level, same everything. So their baseline hazard are exactly the same, H0. But the only thing different is that one group of people, say, take vitamin E supplement. The other group doesn't take vitamin E supplement. So when I compare the two groups of hazard, if everything the same, their baseline hazard can cancel out each other. And what is left over is exponential of whatever risk factor involved. And you can add a lot of other stuff, beta 3, beta 4, but whatever you add, if everything else is the same, they will cancel out each other. Upstairs, downstairs will cancel out each other. The only thing left is what? Oh, one group take more supplement, something more than the other group. The difference between the two groups dictate how dangerous or how much risk or hazard can be reduced. That's why we call this proportional hazard function, because we try to figure out this by using the comparison. So as such, okay, I already told you guys we have three different ways to evaluate risk. One, just by looking at the risk function, the hazard function. What kind of shape? Say, oh, increasing, decreasing, young, die young, or die old. And that we usually call live test. And live test, SAS will have a procedure to help you look at the shape. The other is modeling the survival time. That's called live regression. And the third one is what we call proportional hazard function. And proportional hazard function is comparing the proportional hazard, the risk, the ratio between the two. And as such, we also say that if you just look at the shape, the live test in SAS, PROC live test, is non-parametrics. Why is non-parametrics? Because you just recognize the shape. And then if you're using live regression, you're really doing the regression based on the life. and this is called parametrics. And finally, there's a one, you don't know everything. You don't even need to, here, let me get back here. If I only compare two groups, one group is doing something different from the other group, like a control study in medicine. For example, one group have the COVID shot in the early stage. One take it in the late stage, and which one is more hazard? Then everything's the same, except that they're taking the shots at different time. Since they're doing things exactly the same except that one, so all the baseline hazard are the same. They cancel out each other, so I don't need to know what is their baseline. I don't need to know anything else. All I need to know is that there is a little bit of difference on the handling one particular risk factor. So this is called semi-parametric method, because why is it semi-parametric? I don't even need to know what you're talking about. All I need to know is that here are two groups of people. Their exposure pretty much the same. Nature and nurture pretty much the same, except on this item, one got X1 dosage, one got X2 dosage. The dosage difference dictate their hazard ratio or their proportional hazard. So this is called semi-parametrics. Does that make sense to you guys? Okay, so now I think we've done enough of the theoretical review. It's time for us to play with the first problem. Okay, and this first method is broadly used in reliability and in survival analysis. In reliability is called product limit. In survival analysis, in human life or in a biological system, is called Kaplan-Meier. But two methods exactly the same. Just engineering name it one way, the clinician name it a different way. Second thing is that when we do this, you don't have the luxury to have tons of observation like doing a SAS simulation. Your random number not going to work anymore. We have to use whatever data available. So this method, you need to understand those simulations, but we're using those simulations to help you figure out what this thing's going to look like. Okay, so first problem. Here are 12 people. Okay, I have 12 soldiers. So far, so good. 12 soldiers lined in one row at the starting line. And then, the marshal said, go. So step 0. How many people dead? Nobody died. How many fell at time t? Nobody. Risk at time t means that there are 12 people risk at time t. So far, so good. I'm still at here. And then if nobody die, okay, the survival Q here, here is the failure here is 0, and P equal to 1 minus Q is 100%. So at this point, survival function at T, okay, you don't need to put a plus sign here since we don't have censorship. It's 100%. Everybody understand the first row. It's just star 1 and 0. Okay, now move to time 1. Nothing happened. Since nothing happened, no event will be recorded. At time 2, one event happened. What is that event? Somebody died. So at time 2, one died. So the total at risk, copy from upstairs. Originally, I have 12 people, 12 soldiers, 12 patients, 12 machines at risk. One of the machines in trouble. So the probability of that which one? Okay, now you're basically said that, you know, mini, miny, mo, 12 of them. Which one should be in trouble? You pick one, so whoever got picked is 1/12 opportunity get picked. Agree? So if you have 1/12 get picked, the other, let me get out over here. Let me use Excel. Okay, so if I have 12 get picked, how many survive? Is 1 minus 1/12, or 11/12. Agree? So 11/12, we can double check here, equal to 11/12. Oh. Okay, so if you change the resolutions, it's exactly here. Okay? And here comes something tricky. Your survival function is you need to use your upstairs number multiplied by your Q value. So this will equal to this guy upstairs multiplied by this guy is 0.917. Okay? And why we need to multiply that? Because this number, people think about it. If here is 11, the denominator is getting smaller and smaller, right? Because we have more and more people die. And so this number getting smaller and smaller. People, when you use a very, very small number multiplied by a very, very small number less than 1, this number will shrink until almost 0. Means that there's nothing left. Okay, so by looking at this, we wait at time 3, immediately another event. So since I have another event, I have one more failure. But now, look at this number. Why this number is 11? Rest at time 3, I have only 11. Anybody? Young man in the back, why I only have 11? Yeah, so at time 2, I have 12. But after time 2, I already have 1 already gone. So I only have 11 can play the game. So now, only 11 play the game is 1/11. So here the value, you can also do this, is 10/11. Okay, so I have the 909 coming out. Okay, and let's keep doing this. Okay, next time, this is important. Time at 6. Okay, so time at 4, nothing. Time at 5, nothing. Time at 6, tragedy happened. Not only I have an event, I have 2 die at the same time. So since I have 2 die at the same time, first of all, only 10 left because I have 2 events already. But for the 10 people, this time I will have 2/10 because there's 2 people die. So I'm using 2/10, so it's 80%. And then look at the value here. Start from 100%. Okay, so I can do it this way. Let me do it this way. The survival function, you really can write it down as this. Okay, start from 1, and this number is always equal to upstairs number times the current value. So if you do that, ooh, what happened? Oh, I know. Here, redo it. Let me create this value first. This value is equal to always ST value increase at here. That must be a typo. That's mission impossible. So let's double check. Hey, I used this slides in the last, I don't know how many years. Nobody raised their questions. Huh? Okay. So 1 minus this. Okay. Okay. And this is basically the p-value, right? And then let me do my s value. And my s value start from 1. And this is always equal to this guy times this guy. You know why I said it's mission impossible? Because you multiply by a value less than 1, there's no way that value can. Okay, so let's just put this and said, okay, let me do this one more time, equal to this times 1.000. Okay, 91725, 166.25, 1667.83. The typo happened, yeah, I should move this up, and then I should add one more. Yeah, does that make sense? Yeah, okay. Man, if I do this, I cannot give you this one as an exercise. Okay, but what I prefer you do this is, now let's finish the whole things first, and then, okay, and here is the things I would like you to look at, okay? If you look at this function, insert, and okay, it will drop until it drops to 0, right? Okay. So let me give you an exercise here, okay? Easy. Let's have the time of death. Okay. Everything the same except the time of death equal to the original time of death plus 3. Okay. So now the event time is different. First of all, let me ask you guys this. If I change the time by adding 3, okay, do you think that will change the shape of the survival function? I'm just shifting the entire step functions right, 3 point to the right, right? So if the shape of the survival function is not changing, okay, the slope of the drop back to here, okay, insert. By looking at this, people see the dropped. It dropped quick at the beginning or dropped quick at the end. I think it dropped quicker around here, right? You see that? There's a, yeah, good job. Yeah. So people, what I'm trying to say here is that if I want to see dropped, moving them equally, okay? The dropped, by adding 3, I'm just adding the survival time, but it doesn't influence the dropped. So Victoria, since you gave me the answer, let me ask you this. How can I change the survival function? In other words, is that, okay, for example, okay, here. Everybody agree with me, adding time, 3, to every event, not going to change the shape, right? So if I said that, hey, you know what, I give you the magic hand, you can manipulate this to make this look like it's a child disease, okay? If I want you to make this look like a child disease, how should you do it? You should have more frequent drop at the beginning, or you should have more frequent drop at the end. So in other words, if at the beginning I'll add the time, very little, I just add 1. Okay? But I will add 3 at the end. That means what? If I look at this things, the drop here. Let me. I really need to do something now. Survival. Oh, come on. Come over here. Control C, Control V. Okay, so if this is a survival function, insert has recommended char. This one? This one? No, I want to show that, yeah, this is the right one. They recommended the right one. So look at here, okay? The hazard drop, but slow down a bit, right? And I'm not interested in showing you this. I'm interested in showing you what if, okay? I'm using this one. Put a 0 in. If I use this one, okay? Huh? I have to paste value. Okay, so you can tell it's slowed down, not as much, but coming down steeper. So if I can do this even more, okay, is equal to, no, I don't want to do that one. Your turn, young man. This time I want you to have a bad for senior. So in other words is that I don't want to have too many events at the beginning, but I want to have a lot of events at the end. How to do that? The gapping here increasing, and then so here I will equal to this guy's. No, I will equal to original time equal to this guy, so not changed there, but equal to this guy plus say 0.5. Or no, just add 1. So at the beginning, oh, I'm sorry, we want to dilate, right? So here we will have at 4 or 5 at the beginning, but then at the end, and suddenly copy, well, say to 1. What did I do wrong? Oh, I have a time flipping here. So let me have a 10, no, let me have a 9 and 10 here. Yeah, you want to have the drop more at the end. That means that there are more events at the end. So based on this, okay, let's say that you're working for an evil pharmaceutical company, and you claiming you come up with this magic medicine to treat cancer, whatever cancer, okay? So what would you do to improve your survival rate, to make it look nice? Yeah, so you basically try to figure out that, anticipate something, someone, somehow is not gonna make it's gonna create a drop. If you say that, oh, there's a side effect of this, at age 25 or 30, man, there will be event. What do? Send them home. Because if they're home, you say, oh, they decided to take alternative medicine. They're not gonna work in this study anymore. So suddenly, the intense event will disappear, and then you can, get the FDA approval if nobody watching you, and you'll fool the whole world. And anything happen like that? Any snake oil in human history ever happened? Many times. Okay, so modern medicine, what's important is to watch study like this, but what are you watching is, just by looking at this table, is control when to have the event. If the event intensifies, you just drop. And then you know something's bad. But if you let them slow down, it's not bad. Okay, next. This is how to draw the curve of the test. Okay, what I call a step function. How to do that this time, I'll show you. The trick is this. First, okay, let me do it one time. You copy the time and the survival function, Control C. Let me find a new page. Do it in a new page. Okay, we need to generate this step function the right way. Okay, so you do it this way. Page special value. Okay, and you only keep the first column, the time, and the event, survival event. And after you do this, copy this value and do it one more time. Okay, and once you do this value one more time, you highlight this whole things. You follow me what I'm doing so far? I copy the time of the event and your survival function, you copy and paste twice. So you do this. Once you do this, okay, you can sort data. Sort, okay, expand, and then sort by a column from smallest to the largest. Once you do that, get rid of the first one. And then once you do that, you plot this, okay? Recommended plot. Okay. Hold on. I haven't done the right way yet. After you do that, you need to move down one value. Okay. Let me first make sure it works, and then I'll show it to you. Okay, here we go. We have our step function done. So let me do it one more time. Control Z, Control Z, Control Z, Control Z. Okay? you've done this, you need to have 0, 2, 1, 1. So you just drop this, the last column down 1, shift 1, and then just draw the middle part. That will generate your step function. And what does this step function really mean? Okay, is we basically said at the beginning is 100%, and 100%, 100% until time 2 dropped. And then after time 2 is 0.917, 917, the survival function is 917 until you have event 3. Time 3, another dropped. So every time you basically said that I have a plateau time. This plateau time will last until last event. And why I'm talking about this is, so this will basically show you if you have a lot of drop, 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 that means what? Event, 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 event. That's no good. But if you don't have a lot of event, 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 you should have a long plateau. Follow me? So long plateau in survival analysis or in any management is what? No news is good news. So we don't want news. No news, no news, no news. But if you work for some evil empire, the emperor doesn't want to hear bad news. So what do you do? Kill the messenger. Whenever the messenger want to deliver the bad news, go home. I don't want to hear you. So if you don't hear the bad news, that will elongate longer and longer. Because if you don't send them home, you don't treat a messenger, it's going to have another drop, drop, drop. No matter drop at the beginning, drop in the middle, or drop at the end. Drop, 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 it's no good. From survival analysis, no news is good news. Flat is good. See that? Okay. So now, let's start doing some evil stuff. Okay? And this time, we're still doing it, but the right way. And I'm going to show you how to censor people. Okay, time to death at time 0, nothing happened. 12 people, 1. So first column, exactly the same like before. And then at time 2, at time 2, 1 died, and then it dropped to 917. That's correct. But at time 3, see the plus sign after 3? Plus means that we send them home, or they censor, they check out. So why we put plus? Plus means that before they check out, they alive or they die, they're dead. When they check out, they're still alive. So we don't know after they check out how long they last. Could be 3.1, 3.2, could be 3 plus 30 is 33. We just don't know. But so we put a plus sign there, means that, hey, after they out of the system, I don't know how long they last. So if you put a 3 plus there, that means that this is a non-event. This is called censorship. And once it's censored, see the failure in the previous slide, we put 1 there, right? Here, do you see 1? No, you put 0. Means it's not an event. This guy's out. Okay? So this guy's out, but look what happened. Does this guy out change your total number of people in the study? Still changing the total number of people in the study. Okay? So the ratio here, Q is 0 divided by 11, and here's 1. So from here to 917 to P minus this, you basically said that, oh, if it's a constant, the survival need to be maintained. Because I don't know what happened after that. And if that happened, look from here to here, did you create a tiny plateau by saying number 3, nothing happened to you, you just went home. So here is a plateau, and here, if I have another at time 10, okay, well, after that, we're still back to normal. Time 6, have a 2 event, so 2 out of 10 die in 0.8, 0.38. But here, the value is not drop to 3734. It's 917 flat to 0.734. So we totally change the shape of the survival. We change the shape of the survival. We change the drop of the survival. We change the level of the survival. And what is your hazard function? Hazard function equal to FT divided by ST. Now you're changing the FT, you're changing the ST, you're changing the entire HT. Supposed to be very, very dangerous. We don't want to tell people it's very, very dangerous. Say, nothing dangerous. Why? All the people in danger, we send them home. Censorship is a cheating mechanism in many cases. Of course, I'm playing devil advocate here. If you're talking about an honest study, it could happen. Sometimes people say that, especially right now, terminal ill, people say, oh, I don't want to stay in hospice or any pain management, I just want to go home. Well, there are a lot of forecasting predictions saying that within the next 20 years, there will be precision medicine based on genetic engineering to treat cancer. A lot of terminal, terrible cancer can be treated. And of course, people want to jump on the bandwagon, and how likely somebody just got too much kickback from a pharmaceutical company and fake a study. It could happen. Okay. Now, well, some things. You guys know what happened to Volkswagen, right? What happened to Volkswagen a few years ago? They fought their exhaust for their diesel. Yeah, and so we're talking about Volkswagen, the German pride. Things could happen. Okay. Well, same thing happened to Toyota, and several Japanese manufacturers. They also cook their data, and of course, when you cook your data, you'll see a plateau. Okay. So now here's another plateau, and once you do this, okay, whenever you have the plateau, your Q value equal to 0, your P value equal to 1, and remember, S equal to what? The previous value times your neighbor value, right? So 917 times 1 equal to 917. That's how you maintain your ST, right? Here, 0.6242 upstairs times next value is 1, so you end up with this value, okay? So yeah, here I did it exactly the way, just computationally. Yeah. Oh, by doing this, young lady, your turn. Is it possible to generate a non-monotonic drop? Would it increase the ST value? Because the largest value you can multiply is what? Is 1. So if you multiply by 1, you just keep it at the same level. Okay? The only way you can drop is to multiply by a smaller than 1 value. And of course, you drop. Your goal is dropped until it's dropped to 0. Okay? So once you do that, now you can do the same tricks, copy the time and ST, do another step function. And when you drop the step function, you can add the star. And you add a star onto the curve. The curve. You basically said that, oh, that's over there. There's a event. That event is a sensor event, not a real event. So what will be a smoking gun for you to say, hey, somebody cooked data. This data doesn't look right. Whenever you see a nice plateau, And on the nice plateau, guess what you see? You see, you see several stars on it. That means that how did you generate a star? Because you send a bunch of people home. And if you are auditing for the NIH or whatever, you look at raw data, you basically said, you have great discovery or no great discovery. That's a different story. But first, I want to make sure that you collect your data in an honest way. So a lot of time, you're looking at the drop, and whenever you see a plateau, you say that how many people sensor here. Okay? So, Victoria, let's generate another. Oh, I apologize because I have ABAT review coming in, and I have new equipment I have to set up. So, I haven't graded your last homework yet, but I'm gonna grade it very soon. And my thing is that I think the last homework is the homework really challenging, need to be checked. The previous two kind of copy paste what I did. The likelihood you did something terribly wrong is not high. But last homework deserve I pay attention to it. Okay? So Victoria, let's generate another homework this time. Okay? Repeat the study and create two censorship at different time rather than the time 3 and 10. Okay? I just want to just create two sensors at different time and compare same thing, your drop function with the previous function, and tell me if you can use the plateau. Well, let me go back to the original data set. No. Time of death, leave it as it is. There are 12 events anyway, right? I'm just saying that the two censorship events use different time for censorship event. You guys decide when. The things that I would like you to think about is that how to elongate well, think about it this way, okay? If I can have this this plateau or this plane last long, that looks like what? And nobody died at old age, right? Right? If I can elongate this longer and longer. So when should I do sensor? Do it at the very, very end. If I do it at the very, very end, this thing's gonna last, hey, 20, nobody died, 25, nobody died, 30, nobody died, 32, nobody died. That will make this kind of like, hey, once you pass the initial dangerous stage, everything looks fancy. And if you want to, yep. No, because at the end, your denominators, you only have one and one left. Okay, and the only thing is that, well, let me put it this way. Actually, play at the very, very end, I think is too up. What I'm saying is that if I'm working for a pharmaceutical company and I'm cheating, I won't do it here. It's too obvious, too easy to get caught. If you want to do it, you kind of want to spread some. It's kind of like inch in a little bit, inch in a little bit, inch in a little bit here, inch in a little bit here. Well, for example, would you consider here is the troublesome? Drop too quick. So if I can have a censorship right here, that will make it longer and then drop, right? You follow me? People look at the slide. See here? Here is a critical drop, agree? Here is a sharp drop. So what if I can let it last longer and then come down? That will definitely make my number looks, my survival, my reliability looks a little better, right? We'll get into how to investigate and figure out how the number play a role. But so far, Everybody see that? Okay, so next. Same thing next Tuesday. Yeah, I probably on Thursday after my motion analysis install, I'll come down add a little more because this two homework too easy for you. Okay. Yeah, it's just manipulate a simple Excel, nothing. Okay, next I will tell you that Marlboro cigarette, the cigarette company, you know, this is North Carolina, you should know. They play a lot of tricks in survival analysis about how, you know, cigarettes relationship was people, and how they play the event. A lot of time also got this is what we call lefts, you know, have the same starting time, and later we will get into, because everybody starts smoking at different age. Some at 15, some at 16, some at 20, at different age, and then die or survive. So how to investigate, you know, you can do two tricks. One trick is pour everything in. So you have a timeline and say pretend. You guys follow me? People start and end at different time. So I just said that it's almost like I have a bunch of spaghetti, some long, some short. And then I just say, hey, tap, tap, everybody start at the same point. Make all the spaghetti, at least on one end, it's aligned to evaluate them. And there's another trick you can do. This is what we call accelerated testing. Okay, I will give you more about survival time on accelerated testing, more story. I will talk about Harley-Davidson later, but now I'll just tell you one I actually encountered when I was in grad school. When I was in grad school, Ronald Reagan, still president, and he proposed, you know, Mr. Gorbachev, tear down this wall, the Berlin Wall, and guess what kind of military competition he come up with? He actually come up with a lot of military competition with the Soviet. There's one more. He called it Star War. And what is Star War? Is this killer satellite in space, and this killer satellite can shut down the Soviet satellite, can shut down the Soviet's, cruise missile. So that's, to the Soviets, this is very, very scary. And the problem is that it's a promise to have this laser beam up in the space, wait for 20 years, and then suddenly says that, okay, fire. Now, people, is the space a very harsh environment or is it a very calm environment for electronics? It's a terrible environment, you know, solar wind, or you know, temperature is very hot, very cold, and of course you won't get rust since there's no oxygen up there, but it's very bad environment. Now, can you design a weapon system and say that, let me wait 20 years and see if it will still work? You cannot wait that long. So what the accelerated testing basically says that, let me create a simulated space, and then I will use very, very short period of time, torture the satellite back and forth in all kinds of possible risk factor, and then I turn the, you know, slow, grow, and that into a slope in a different rate. So if I grow and die in a different rate, my calendar time is a flat calendar time, but my accelerating testing, I can figure out my survival ability, draw those step function in a different ratio. And this is called accelerated testing, and that's another way to deal with the time. Okay, see you next time.